A stationary man is standing in the rain. The rain falls with a speed of 8 meters per second at an angle of 30 degrees with the vertical. So the rain is falling in the southeast direction. Since the man is standing stationary, the velocity of the rain with respect to the man will be identical to the velocity of the rain with respect to the ground. This is the case only when the man is stationary. The man now begins walking to the right, and he walks at a speed such that the velocity of the rain with respect to the man now makes an angle of 30 degrees with the vertical, but in the southwest direction this time. Mind you, the rain continues to fall at 30 degrees with the vertical in the southeast direction as before, but due to the man moving, the velocity of the rain with respect to the man now changes. We have to find the speed at which the man walks. So in this vector diagram, we have to compute Vm. If you look at the vector diagram, you will see that the vertical dotted line virtually splits the vector triangle into two equivalent right-angled triangles, and therefore the angles the vectors VR with respect to M and VR make with Vm would be 60 degrees. We have to find the magnitude of the horizontal blue vector Vm here. Since this is an equilateral triangle, the magnitudes of all three vectors will be the same. We are already given that the speed of the rain is 8 meters per second, so the magnitude of VR would be 8. Therefore, the magnitude of vector Vm would also be 8, since this is an equilateral triangle, and the man has to walk at 8 meters per second to the right if the rain has to strike him at 30 degrees with the vertical in the southwest direction. So with all the problems that we have solved so far, you have seen the importance of the vector diagram. Once that is done, we simply use triangle properties to solve for the unknown. This was also an interesting case where the rain comes down in the southeast direction but appears to be approaching a moving man in the southwest direction.